This lecture. I'm thankful to Melvin, my big friend, and so thank you so much for invitation. Let us start our lecture. We'll speak today about order in biological patterns, their sources, informational origin, and the principle of Landauer. What is the outline of our lectures? First of all, we will introduce the main notions. Main notions are periodic or aperiodic ordering, and we will discuss physical and also biological rules of symmetry and asymmetry. We will very briefly discuss the generalization of Curie-Neumann principle as it applied to biological laws. And we will try to understand two different approaches to the order and symmetry in biological objects, which are called up-bottom and bottom-up physical approach. We will demonstrate very interesting thing from pure mathematics point of view, that we have no unique mathematical measure of ordering. The notion of order and ordering has a fine structure, and it's a very important conclusion. And we will speak about informational / algorithmic roots of ordering, which are inherent for biological systems, and about applications of the Landauer principle, which I believe is known to our, and we will introduce some perhaps philosophical principle of informational parsimony, which I think is highly relevant to the realm of biology. The main goal of our lecture is establishment of interrelation between order, symmetry, and information. You see, we'll deal with main notions of modern science: order, symmetry, and information. And we'll try, of course, to the first attempt to understand how does it work in the field of biology. What are main questions to be addressed in the course of our lecture? What is order? What is the meaning of the word order and how it may be quantified? And why we recognize numerous examples of order inherent for biological origins. Let us start our lecture. It is well known that biological objects, see this butterfly, please, they demonstrate unbelievable symmetry and regularity on various special scales. It's a very interesting thing. Even biomolecules are already symmetrical, and the entire organism is also symmetrical. And the main question to be addressed, and possibly we suggest some alternative answers to this very fundamental question: why biological objects are symmetrical? And we also see that we have some fine structure of answers. First of all, in biology, we recognize very different kind of symmetry and ordering. Now, it is well known that a lot of organisms demonstrate bilateral body symmetry, and sometimes we can see the rotational five-fold symmetry, as we see in this picture. And it is generally, it is very general picture. We recognize all kinds of well-known physical symmetries in biological objects: rotational symmetry, translational symmetry, mirror symmetry, and it is very interesting, even asymmetry objects which demonstrate no symmetry. We will address also this problem. Let us start from the smallest possible spatial scale. I mean, of course, biomolecules. We have a very recent research, very fresh research, which demonstrates that 40% of biomolecules already demonstrate different kinds of symmetry. This is the smallest biological scale. We speak about proteins, biological molecules. I strongly recommend to see this very interesting. So we recognize symmetry or ordering on this small scale and also on different scales, special scales which appear in biology, up to entire organism. And as I already said, people from biology generally agree that there also exist organisms which demonstrate zero symmetry. These sponges that you see in this image demonstrate zero image. I first of all think that it is not so exact question, but we'll discuss. So we see some order and some symmetry, and let us now address the main question. What is symmetry? We know exactly. It is a well-defined mathematical operation. We know what is symmetry, it is well-defined, and we agree what is symmetry. But the much more problematic notion is the notion of order. What is order and what is disorder? And we have very interesting, essential progress in this field, which was achieved in 2010, last year. So I strongly recommend this paper, which is referred in my presentation by Macha, The Role of Aperiodic and Aperiodic Order in Science and Technology. Very good paper and very deep understanding of the. First of all, we have to distinguish between periodic order and aperiodic order. What is the periodic order? When we have some motif and some repeat mechanism, this is classical situation which is well known in crystallography. What is a crystal? We have some unit cell and it is translated infinitely, and so we have periodic. A very different kind of order is aperiodic order, and it was not addressed until now. Now people work much on this. A very good example of aperiodic order is sunflower. It is well known to people from biology that the spirals in sunflower are ordered, but they are ordered in a periodic way. So first of all, we have to understand we have periodic and non-periodic ordering. Very good example from physics, not from biology, is ice. We have 7 or 6 kinds of ice. This depends on exact definitions, but some of these structures are periodic, and the right one is aperiodic. Here we have aperiodic ordering. So we have periodic and aperiodic ordering, both in physical and biological. Okay, let us now pose the very fundamental question. How to measure, how we can quantify order. What is the mathematical measure of order? And now it turns out that the answer to this very fundamental basic question is not simple, and it already has a fine structure. First of all, I introduce this idea we have to distinguish between physical ordering and mathematical ordering. And it is not the same. It is not simple, but it is not the same. Physical ordering, they regularly, traditionally quantify with the so-called Boltzmann entropy, which is well known for physicists. Here is the famous Boltzmann formula. And it is well agreed in society and in the physicists that it measures ordering. The thermodynamic state with with great entropy is regarded usually as disordered. You see this in this slide, and the ordered thermodynamic state is quantified, is described by small u value of entropy. Okay, now I will show one of the main results, which is not obvious from first glance. When we speak about order, it is very important. We usually don't speak about entropy. We speak about symmetry of the object, of an object or pattern. And we concern the pattern as ordered, if it is symmetrical. It demonstrates symmetry. And there, it is very interesting that there exists very interesting interrelation between symmetry, order, and entropy, traditional Boltzmann entropy. A very good story about the symmetry is told in the famous Feynman lectures of physics. There's famous Nikko gate in Japan, and Richard Feynman wrote, "Why nature is so nearly symmetrical?" And the answer is, well, no one has any idea why. The only thing we might suggest is something like this. Here is a famous Nikko gate in Japan. This gate is very elaborate, has a lot of figures, but when one looks closely, he sees that in complex design along one of the pillars, you recognize some elements which come upside down. If one asks why this is, the story is that they come upside down so that the gods will not be jealous about perfection of man. This is some poetic description which I like very much. Indeed, the role of symmetry and ideas of symmetry in basic physics is tremendous. The conservation laws actually follow the symmetry of space-time. And we have, I already mentioned it, that we have very, very well definition, rigorous mathematical definition of symmetry, which is defined as a property of a body by which the body can be brought from initial state to another indistinguishable state by means of a certain operation which is called a symmetry operation. But order and chaos are very different. They are obscure notions, which are, to a much extent, are rooted in the human psychology and hardly could be accurately defined. Now, we want to show that when we speak that something is ordered, it actually means that the object is symmetrical. And this symmetry, in turn, influences the entropy of the system. Again, we speak about the traditional definition of entropy as it was given by Ludwig Boltzmann. I addressed the simplest but extremely useful physical system. What do I have here? Scroll. This is the system of spins which are immersed in the magnetic field. If we have some system of fields which it is absolutely disordered, we have no symmetry, we have this situation. But if we impose the mirror axis of symmetry, immediately entropy is decreased. And this is true for different systems and different operations of symmetry, twofold, fourfold, it doesn't matter. You can see details of calculations in this paper. Even we have more simple example. For example, we have this system in which we have chamber and 4 molecules. And if we impose symmetry on the system, the entropy of the system is simply 0 because there exists only one realization, micro-realization of this macro system. And I tried to do it with different difference of spins. And the general conclusion is extremely simple and is clear that introducing of symmetry decreases the entropy. It doesn't matter what is the spin excess energy of the system and value of magnetic field. And this is true for different kinds of symmetry, four-fold, six-fold symmetry. It absolutely doesn't. This is true for physical symmetry and physical ordering of the system. We have system of spins. This is real physical system. We have exactly defined Boltzmann entropy. And when we say that the system is ordered, actually we say that it is symmetrized. We have some symmetry in this. A very different situation we have when we speak about mathematical patterns. We have mathematical order, and we will see now, it's very interesting. It is not expectable also that mathematical order may be quantified by very different and even, it is more important even, non-correlated measures, which are Voronoi entropy, continuous measure of symmetry, and Shannon measure of symmetry. The first idea emerges from my suggestions, which were suggested by René Descartes, and now it is called Voronoi tessellation and Voronoi diagrams. Actually, we can see Voronoi diagrams already in papers by René Descartes. What is a Voronoi tessellation? This is a partitioning of plane into regions based on distant to discrete set of points, which are called seeds. And for each seed, we have a corresponding region consisting of points closer to that seed than to any other. Today, we have a very well developed software which enable us to build immediately for any set of seeds the Voronoi diagram. This is a page from René Descartes' book in which he posed, as already Descartes did, the most fundamental question. We have stars on the sky. Are the stars ordered? Do we have order? Are the great masses of stars ordered? And actually developed the procedure which is today called the Voronoi tessellation. Voronoi tessellation yields us the notion which is called Voronoi or Shannon, perhaps will better denote the Shannon entropy, which is defined according to this formula, this equation. The n is the fraction of polygons with n sides and edges in a given program. If we have only squares or only triangles, the Voronoi entropy is exactly zero. It is very simple Shannon entropy because we have fine kind of your polygons. If your pattern is built from polygons of the same kind, the fraction is 1, ln is 0, and we have 0 Shannon over it. If we have fully random distribution of seeds, nuclei, whatever, we have the largest possible Shannon entropy, 1071. As a matter of fact, nobody knows what is the source, mathematical source of this value. We're trying to understand it, but it turns out it is not simple. So generally, Voronoi entropy of some pattern is close between 0 and this maximal value. In literature, we have much problems today with Shannon-Voronoi entropy and Boltzmann entropy. People do not distinguish between these notions. They are very, very different. It is important to emphasize immediately that these values are essentially different. Why? First of all, Voronoi entropy is intensive property of the pattern. Thermodynamical entropy is extensive property of the system. If the system is growing, Boltzmann entropy is growing. And this is not true for Voronoi entropy. It's very important. So the historically first measure of mathematical order is given by Voronoi/Shannon entropy, which is defined according to this well-known. Okay. And if we say that order or ordering is synonymous to symmetry, we usually accept and accepted for a long time that symmetry is a binary property. Or the pattern is symmetric, see this picture, please, or it is asymmetric. 1, 0, 1, 0, come con information. Now the situations change dramatically, and I want to recommend here a set of papers by Professor of Nirve, Professor Zabrodsky from Hebrew University, who introduced very interesting idea which is related to quantification of symmetry/ordering. This measure is called continuous measure of symmetry. The idea is simple, but the calculation is not simple, as always is taken. For example, you have arbitrary triangle, here it is. It is obviously not symmetrical. The question is how it is far from to be symmetrical. And Avnir and Zabrodsky introduced following very simple idea. Let us build the equilateral triangle and let us find the square deviations from this triangle. So we obtain already the measure of symmetry, which is continuous. It is already continuous. One triangle is close to be the equilateral triangle, and some triangle is far from it. And we already broken, it's very important, we broken the binary paradigm of asymmetry. This group is working very, very actively, and they publish a lot of papers, and now they applied this idea to very different systems, starting from molecules, chemical molecules, proteins, and even to quantum mechanic objects. We posed very fundamental questions. Let us understand the situation. We have already two measures of order, Voronoi entropy, and we already have the second continuous measure. Are these measures correlated? Do we have correlation always, prescribed correlation between Voronoi entropy and continuous measure of symmetry? We worked with a very interesting object with our colleagues, which is called capillary cluster. What is capillary cluster? You have a cup of coffee. Here is my cup of coffee, and when the coffee is hot, we see a fog here. People really don't know that this fog is actually built of very small droplets, which are ordered. The pattern which we see here is not random. And it is very convenient from the mathematical point of view to work with this object. We have droplets. The center of this droplet is our seed or nucleus in Voronoi diagrams. And it is very easy to build in parallel continuous measure of symmetry and also Voronoi entropy of this system. And we were extremely surprised when we recognized that these measures are not necessarily correlated. These measures are not necessarily correlated. Moreover, they may characterize your pattern in antiphase. We have patterns with big value of Voronoi entropy and small value continuous measure and vice versa. It's very interesting, and it was really very surprising. We published already some papers about this idea, and this is very important conclusion. We have two measures of order/symmetry. They are Voronoi entropy and continuous measure of symmetry, and they are not necessarily correlated. We also tried to analyze very famous pattern which was created by Roger Penrose, Nobel Prize winner. We took the Penrose tiling and calculated with software in parallel Voronoi entropy for these patterns and continuous measure of symmetry. The results were recently published here. This is one of the patterns. It is built, you can see here from figures, in such a way that we have the Voronoi/Shannon entropy, which is exactly zero, but it is very far from to be symmetrical. So the Shannon of Voronoi entropy is exactly zero, but continuous measure of symmetry is very, very high for this. So this strengthens, this research strengthened our conclusion that the continuous measure of symmetry, and the Shannon entropy of the pattern mathematical are not necessarily correlated. And now the most perhaps interesting point, we speak about the biological system. We have very different situation in biology. In physics, for example, in crystals, symmetry and order are perfect. We have ideal symmetry in crystals, when we speak about ideal crystal, of course. But in biological rooted patterns, symmetry is never perfect. And now people from physics and biology introduced very interesting ideas, and one of which is the idea of fluctuation asymmetry. But the main and fundamental question is why we have symmetry in biological patterns? Why there? Why we have symmetrical structure of body of animals and so on and so on? Why? What is the reason? Generally exists today in literature two very different approaches. The first is biological approach. And the people from biology accept that ordering in biological patterns in the structure of the body, for example, have pure survival reasons. And it was demonstrated for these birds, for example, zebra finches, for example, that symmetrically banded males produce more offspring than non-symmetrical ones. For example, the idea is biology, survival idea. Now, absolutely different idea was suggested, of course, by physicists. People from physics suggested physical reasoning for the symmetry of biological patterns. And now we also have some fine structure of the physical reasoning. We have top-down approach, which suggests that we adopt in this approach that the symmetry of biological object is dictated by media in which the structure is functioning. For example, in such a way, people from physics try to explain the symmetry of fishes. In other ways, bottom-up approach, assuming that the symmetry of biological structures emerges from the symmetry of molecules. Biological objects and physical objects are also built from molecules. Molecules have some symmetry, and this symmetry appears also on larger spatial scales. In this context, very interesting ideas were suggested by Pierre Curie, and they are called as Curie-Mennegerode-Neumann principle, which absolutely is not biological, it is a pure physics. Curie suggested that the group of a structure of crystal contained in group of each physical properties. We have some microscopic symmetry on the microscopic level, and we have some macroscopic structure, macroscopic properties, and macroscopic structures reflect actually the symmetry of microscopic properties of the. And Curie already suggested or understood that symmetry is important, but in certain cases, the most famous example is piezoelectricity, of course. Piezoelectricity appears only we have breaking of symmetry. Symmetrical crystals do not show piezoelectricity. As Curie suggested in such a aphoristic way, formulated the asymmetry is what creates a phenomenon. And we think that this is also true and maybe expanded for biology, and symmetry is what creates a biological phenomenon. So we already have two physical ideas that explain appearance of order in biological orders, and one more idea, it is a recent idea, is informational reasoning, which explains abundance of symmetry in biological things. And it is suggested in our paper and other papers that symmetrical biological structures arise not just to the natural selection, not just by physical problems, but they require less specific information and, consequently, according to the Landauer principle, less energy to encode. We speak in Informational Institute. I suggest that people know what is the Landauer principle, that there exists. So very briefly, a minimal possible energy required to erase 1 bit of information. It was suggested by Landauer and developed in a number of recent papers. I strongly recommend, for example, papers by Melvin Wobson devoted to the problem. And as a matter of fact, the very deep roots of this idea go to John Archibald Wheeler, one of the most unbelievable physicists of 20th century, who suggested this basic, fundamental physics should be rebuilt on informational groundings. And Wheeler suggested the main notion of physics are rooted in the bit-based scientific paradigm. And aphoristically said, it reduced from bit. But what do we have in biology? While Landauer principle may be decisive for biology, why? What is the reason? We see a sunflower and sunflower spirals, and sunflower spirals are more or less exactly described by Fibonacci series. It is very long, very known observation. What is very important, I think, in this connotation? The algorithm of Fibonacci sequences is extremely short, extremely effective, and informationally effective. We need a very small amount of bits of information in order to write this sequence in the DNA code. We have to understand very clearly that in DNA, we have restricted volume of information. And we have to write in this code everything about our sunflower. So nature in this connotation prefers short, effective, and simple algorithms. There is nothing more simple than a Fibonacci series algorithm, of course, which is written here. So we introduce the idea of informational parsimony, economy. Nature, in very different situations, prefers not survival foundations, but informational foundation. In a very restricted volume of DNA, we have to keep a lot of information. So we need very short algorithms. And a very good example of the shortest possible algorithm is Fibonacci sequences. This is the idea that we think, of course, it should be tested and tested and tested and checked. But I think it sounds at least as reasonable suggestions. Okay, now we already came and to our conclusions, and we will have, I see, some time for questions. First conclusion, which is extremely important, which emerges from our research, that three main notions of exact sciences, order, symmetry, and entropy, are interrelated. Always, when we impose the system, we diminish consequently the entropy of the system. Very good example for this is the system of an elementary magnet which are embedded into external magnetic field. So these three main notions are interrelated. When we speak not about physical order, which is quantified by Boltzmann entropy, we have very different measures of order. Perhaps the most developed of them are Voronoi entropy and continuous measure of symmetry. And I want to stress it is not obvious. It's absolutely not obvious. They are not correlated, and we even have the situations when they work in antiphase. The maximal Voronoi entropy corresponds to the minimal continuous measure of center. As a conclusion, perhaps the most important conclusion, unique mathematical measure quantifying order in biological mathematical does not exist. When we speak about biological system, we see a lot of highly ordered patterns, systems, colors, so on very different scales, biological scales. Why do they exist? We have a lot of different ideas. We already suggested, but I think one of them, and perhaps it may be one of the most important, is an informational paradigm. It is explained very, very simply. Why symmetry enables economy of information. When you know the location of one spot on your bird's feeder, you immediately automatically know the location of other symmetrical spots. You have an enormous economy, parsimony of information. Correspondingly to this, according to Landauer principle, we have economy of energy. So symmetrical biological structures perhaps do not arise due to the natural selection, and also because they require less information to encode. And there is enormous literature today to read. Some of papers I recommend to read. Let us see these papers. And what we plan to do just now in our research group in Ariel University. First of all, we continue to study interrelation between Voronoi entropy and continuous measurement. The second point is absolutely obscure. Do we have some correlation between Boltzmann entropy and mathematical measures of order, such as continuous measure of symmetry, and Voronoi entropy? Nobody knows answer to the question. And we plan also to continue study of symmetry, continuous measure of symmetry of biological patterns. Thank you so much for your invitation. I am in time, and you have time for questions. Please ask questions.